Hello friends, so welcome to the 26th lecture of this course, and this lecture is again just the continuation of the previous lecture. Here I will introduce few more properties of beta and gamma functions. Again we will take some example and we will solve them in terms of beta and gamma function. So first of all, see this important result related to beta function. So it is saying that the integral over a to b u minus a raised to power x minus 1 b minus u raised to power y minus 1 du equals to b minus a x plus y minus 1 beta of x y, where x and y are positive numbers. So the result is something like that. So integral I equals to integral over a to b u minus a raised to power x minus 1 b minus u raised to power y minus 1 du. This equals to b minus a raised to power x plus y minus 1 into beta x y. X and y are positive. So let us try to prove it. So proof is something like that. We know that beta of x y equals to integral over 0 to 1 t raised to power x minus 1 1 minus t raised to power y minus 1 dt. So this is the definition of beta function we have seen. Now put t equals to u minus a upon b minus a. So this will give us dt equals to 1 upon b minus a du. So from here I can write beta x y equals to t is u minus a upon b minus a raised to power x minus 1, then 1 minus u minus a upon b minus a raised to power y minus 1, and dt is du upon b minus a. So if you notice here, in the denominator I am having b minus a raised to power x minus 1 from this expression, b minus a raised to power y minus 1 from this expression. So it will become x plus y minus 1 minus 1. So x plus y minus 2. But at the same time we are having plus 1 from here. So total I am having b minus a raised to power x plus y minus 1, and I forgot to put limit here. When t is 0, you will become a, when t is 1, you will become b. Integral over a to b So, this will be u minus a raised to power x minus 1, b minus a minus u plus a. So, this will become b minus u, because minus and plus a will be cancelled out, raised to power y minus 1 du, and this thing equals to beta of x y. So, if I take this constant term another side, I will be having this equals to b minus a raised to power x plus y minus 1 into beta of x y equals to this one, and this is the relation which we need to show. So, this is the proof of this particular example. Now, let us see the consequences of this particular relation. If we take a equals to minus 1 and b equals to 1, then what we will be having? Minus 1 to 1 u plus 1 raised to power x minus 1, and then b is 1. So, it will be 1 minus u raised to power y minus 1. So, better let me write it 1 plus u to maintain the symmetry. So, 1 plus u raised to power x minus 1 into 1 minus u raised to power y minus 1 du, and what will be the value of this definite integral? B minus a. B minus a means 1 minus 1 minus 1, 1 plus 1, 2 raised to power x plus y minus 1 into beta x y. So, we obtain another relation in beta function and definite integral. Now, in this relation, if I take x equals to half equals to y, then what I will be having here? Minus 1 to 1, 1 plus u raised to power minus half, 1 minus u raised to power minus half. So, it will become 1 plus u into 1 minus u will become 1 minus u square raised to power minus half du, and in the right hand side it will become 2 1 half plus half minus 1. So, 2 raised to power 0 total. So, 1 into beta x y. So, beta x y will be beta 1 by 2 1 by 2. Now, let us see about this particular integral. Here if I substitute u equals to sin theta, then what I will be having? Du equals to cos theta d theta. So, what integral it will be? When u is minus 1, so sin theta is minus 1. So, it will become minus pi by 2 theta, and when it is 1 it will become pi by 2. 1 minus u square means 1 minus sin square theta, that will become cos square theta. So, cos square theta raised to power minus half. So, basically it will become cos theta raised to power minus 1 into du will be cos theta d theta. So, it will be basically minus pi by 2 to pi by 2 d theta, and this equals to pi. So, what I am having? My left hand side integral is giving me pi, right hand side is beta half. So, beta half equals to phi. Now, if we see the relation between beta and gamma function, so it will be gamma half upon gamma 1 equals to pi. So, it means gamma 1 is 1. So, gamma half square equals to pi. So, from here again we are getting our famous relation that gamma half equals to root pi. So, we ended up with this relation. Hence, we can use this formula in many ways to evaluate definite integral by substituting the appropriate values for x, y and a, b. Okay, so now we will see one more important result, that is gamma x plus 1 approximately equals to x raised to power x plus 1 by 2 e raised to power minus x into square root 2 pi when x tending to infinity, means this relation is true for large values of x, not for small values of x. Okay. So, how to prove this relation? That is a bit tricky. Let me give the outline of this. So, here x denotes a real variable, and we know from the definition of gamma function that I can write gamma x plus 1 equals to integral 0 to infinity e raised to power minus t into t raised to power x dt. Now, what you do in this? Substitute t equals to x into 1 plus u. Then in the left hand side it will remain as gamma x plus 1. In the right hand side, when t is 0, u will become minus 1. When t is infinity, u will remain as infinity. So, it will become minus 1 to 0 e raised to power minus t. So, t is x times 1 plus u. So, e raised to power minus x 1 plus u, and then t raised to power x means x raised to power x into 1 plus u raised to power x, and then you know dt will become x times du. So, this x is coming due to dt. So, dt equals to x times du. So, after this particular transformation or substitution, this particular integral becomes in this form. Now, as you know that this integral is on variable u. So, I can take the terms involving x out. So, I have taken x raised to power x from here, x from here. So, total will become x raised to power x plus 1, e raised to power minus x I have taken out here, and then integral over minus 1 to infinity e raised to power minus x u into 1 plus u x du. Or this I can write that 1 plus u raised to power x I can write as e raised to power x into log of 1 plus u. So, that in this way this particular integral can be written in this form. So, now I am having this particular integral. Now, the question is how to solve this integral. What sort of transformation we should make to find out the value of this particular integral, and on what values of x we can evaluate this particular integral, and so on. So, now let us see this function minus u plus ln 1 plus u. So, let us assume that it is a function of u and I am naming it f of u. So, f of u is minus u plus log 1 plus u. This thing equals to 0 for u equals to 0, because when u is 0 this term will be 0 and log 1 will be 0. For other values of u we have the value of u is negative, because always the value of this particular thing will be greater than log 1 plus u. Hence, for other values of u fu will be a negative function, means it will be below x axis, u axis. This implies that the integrand of the last integral equals to 1 at u equals to 0, and that this integrand becomes very small for large values of x at other values of u. So, the large values of x we only have to deal with integrand near u equals to 0, because it is very small for other values of u. Note that we have fu is minus u plus ln 1 plus u. So, I can write it minus half u square plus terms having u raised to power 3 and higher order term for u tending to 0, means I have expand log 1 plus u. So, this u will be cancel out. So, I will be having terms of second order. This implies the integral over minus 1 to infinity e raised to power x times minus u plus log 1 plus u du is approximately equal to minus infinity to infinity e raised to power minus x u square upon 2 du for x tending to infinity. If we set u equals to t times root 2 upon x, we have the relation minus infinity to infinity e raised to power minus x is u square by 2 du equals to x raised to power minus half, root 2 will be out, minus infinity to infinity e raised to power minus t square dt, and you know that minus infinity to infinity e raised to power minus t square is root pi. So, this becomes x raised to power minus half root 2 pi. Hence, we have gamma x plus 1 which is approximately equals to this relation equals to x into x plus 1 raised to x plus half e raised to power minus x root 2 pi when extending to infinity. So, this is what we need to prove. So, proof is a bit complicated. You should have the idea of log 1 plus u, how to expand it and how to check the value of fu for different values of u and x, and how to write this particular integral approximately equals to this one for large values of x. Now, let us take one more example. It is given that integral over minus 1 to 1 minus t square raised to power n dt, where n is a positive integer and we have to evaluate the value of this particular integral. So, integral is I equals to minus 1 to 1 minus t square raised to power n dt. N is a positive integer. So, I can write I as minus 1 to 1 minus t 1 plus t. So, 1 minus t raised to power n 1 plus t raised to power n dt. Now, how to move? Okay, we can do in this way. Put one plus t equals to twice of u. This will give me dt equals to 2 times du. So, from here I will be having when t is minus 1, u will become 0, 1 minus 1 0. When t is plus 1, u will become 1. 1 plus t is 2u. So, 2u raised to power n. Now, what will be 1 minus t? So, 1 plus t equals to 2u. So, t equals to 2u minus 1. So, minus t equals to 1 minus 2u, okay, and then 1 minus t will become 2 minus 2u, that is 2 times 1 minus u. So, let me write it here, 2 times 1 minus u raised to power n into 2 is coming from dt du. I can take all these 2 outside. So, 2 raised to power n from here, 2 raised to power n from here and 2 from here. So, it will become 2 raised to power 2n plus 1, 0 to 1 u raised to power n 1 minus u raised to power n du. Now, this thing equals to 2 raised to power 2n plus 1, okay. And then see this particular integral, it is, we can equate it with the definition of beta function. So, it will become beta of n plus 1 n plus 1, or n is a positive integer. So, 2 raised to power 2n plus 1, we know the relation between beta and gamma function. So, I can write it gamma n plus 1 upon gamma 2n plus 2. Let us make more simplification in it. 2 raised to power 2n plus 1, gamma n plus 1 is factorial n, because n is a positive integer, gamma n plus 1 is again factorial n is a positive integer. So, 2n plus 2, so it will become factorial of 2n plus 1. Okay. And later on you can simplify it a bit more. So, this is the value of this particular integral. Okay. A few more examples. So, that for any positive integer m, integral over 0 to pi by 2 sin theta raised to power 2m minus 1 d theta equals to this particular thing, that is in the numerator I am having 2m minus 2, 2m minus 4 and up to 2. In the denominator I am having 2m minus 1, 2m minus 3 up to 3. Now, how to solve it? So, basically we need to prove that integral 0 to pi by 2 sin theta raised to power 2m minus 1 d theta equals to 2m minus 1, 2m minus 3 up to 1, or 1 is not make any effect. So, better I will write up to 3. Okay, we know that beta of mn can be written as 2 times 0 to pi by 2 sin theta raised to power 2m minus 1 cos theta raised to power 2m minus 1 d theta. From where I am getting this feeling? Because I need to solve this integral. So, here the term is involving sin theta. So, I have taken this particular identity of beta function. Now, put n equals to half here. So, what I am having? Beta m half equals to 2 times 0 to pi by 2 sin theta raised to power 2m minus 1 d theta. Okay. And if I take this to this side, so it will become 1 by 2 this one. So, the right hand side of this exactly equal to this one. Now, we have to prove that this particular value equals to this one. So, let us try to expand it. 1 by 2 into beta m n will become gamma n upon gamma m plus n. So, gamma m gamma half upon gamma m plus half. Here m is a positive integer. So, this equals to factorial m minus 1 gamma half upon gamma m minus half. Now, what you do? Here if I open this factorial, it will become m minus 1, m minus 2 and it will go up to 2, 1, finally 1 will come. So, total terms are m minus 1 terms. Okay. So, I multiply in numerator as well as denominator by 2 raised to power m minus n. So, 1 2 I forgot here, this 2. So, 2 raised to power m minus 1 in numerator, 2 raised to power m minus 1 in denominator. So, in each term I am multiplying by 2. So, when I will multiplying by 2 in m minus 1, it will become 2m minus 2. When I multiplying in m minus 2, it will become 2m minus 4 and then up to 2 into gamma half upon, here also I am multiplying with 2 raised to power m minus 1 and 1 2 I am already having here. So, if I multiply by this 2 in this one, it will become 2m minus 1. And then in this way it will moving on, I will get the required denominator and this gamma will be cancelled out. So, in this way I will get the relation given in the problem. Similarly, if instead of 2m minus 1 I am having sin 2m theta in the integral, then I will get this result, and this will be obtained in the same way just by taking the value of m plus half and half and following the same process as we are having in the earlier example. So, in this way I will end the beta and gamma functions. Later on we will see the applications of these two functions in multiple integral in next few lectures, where the integral can be directly written in terms of these functions. So, thank you very much.